Welcome back to lesson 3 of the energy changes topic. This is bond energy calculations. This is a higher tier lesson, so if you're doing the foundation tier, then there's no need to continue with this lesson. So the exam board AQA, this is what they say students should know, so you can stop the video in order to look at that in more detail. Alright, to start the lesson, what we're going to do, we're going to just have a look at this exam question here. You should be able to label the things on this slide based on the last lesson when we looked at energy profile diagrams. So if you're in school now, we would spend about 3 minutes doing this, but if you're doing this online or at home, then just take some time to draw out the diagram and then have a go at answering it yourself. Okay, so looking at line A, hopefully you've all labelled that as reactants. And then line B, this is going to be our energy change, or delta H. Okay, we're going to be looking more at that. Line C there, that's our activation energy. So the activation energy is the minimum amount of energy needed for a reaction to happen, and that's very important. D is our products, and as you can see in this diagram, our products are lower than our reactants, so we've actually got a negative energy change, so energy must have been given off to the surroundings, therefore this would be an exothermic reaction. Then line E is our bond making energy. That's the energy released when new bonds are formed. Okay, if you remember, initially we have to put energy in, which is A, the activation energy, and then energy is released when the new bonds form, and that's E on the diagram. So can you define activation energy? I've just mentioned it now, and I've mentioned it previously as well. So activation energy is the minimum amount of energy particles need in order to react. Which line shows the bond breaking energy? Again, I mentioned that a moment ago. On the graph, it would be line C, but in an exam question like we've got here, we would always label line C as the activation energy, but that is actually the energy needed to break the bonds as well in the first place. Okay, but in an exam or in a question, you would always label that as activation energy. Explain whether this is an exothermic or endothermic reaction. Right, with an explanation, we need to give scientific reasons why. So we need to say whether it's exothermic or endothermic, and then because. So this example is exothermic because our products have less energy than the reactants. So you can see that the products D are at a lower energy level than our reactants A. Okay, so that would be your explanation. Right, here we've got two graphs that we saw last lesson, an exothermic example on the left and an endothermic example on the right. What I want you to do is come up with a sentence to explain the difference between exothermic and endothermic reactions in terms of the energy used to break bonds and the energy released when new bonds form. Okay, I've spoken about it briefly when we were just looking at that starter question there, but see if you can come up with a sentence that puts that all into one form where we can explain using bond energies, using breaking bonds and making bonds to explain if a reaction is exothermic or endothermic. So pause the video now to have a go. Okay, I've just moved those two graphs to one side there. So we've got the exothermic one at the top and the endothermic one at the bottom. So we asked you to come up with a sentence to explain in terms of the energy needed to break bonds and the energy released when new bonds formed, why reactions were exothermic or endothermic. So if we look at this exothermic one first, the energy needed to break the bonds is less than the energy released when new bonds form. So you can see I've added two green arrows on there by the reactants and by the products. So the reactants part going up, okay, that's the energy needed to break those bonds. And you can see that that's quite a bit smaller than the green arrow on the right by the products, and that's the energy released when the new bonds form. So we can say here that the energy needed to break the bonds is less than the energy released when the new bonds form. And that's why we end up with a negative energy change, a negative delta H. Okay, so if you imagine that up arrow was 100 and the down arrow was 200, 100 minus 200 would give you minus 100 as your energy change. So the endothermic graph. This time, the energy needed to break the bonds is more than the energy released when new bonds form. So the arrow on the left by reactants there is quite a large arrow. That would be our sort of 200 arrow this time. And then the arrow over on the right for the products, that's a smaller arrow, and we could say that that was a value of 100. So 200 minus 100 would give you a positive value of 100. So your delta H would be positive in an endothermic reaction. If you haven't already, just note down those two examples and explanations now. Right, last lesson we saw this slide. Okay, so we spoke about how the energy profile diagrams, we could see the reactants and products had a certain amount of energy. Okay, we can see those flat lines on the graph. But what is it in the reactants and products that contains the energy? So last lesson we learned that the bonds between atoms and ions contain energy. So different bonds contain different amounts of energy, and that energy is measured in kilojoules per mole. So we've got a new term now. So we've got bond energy. So the energy needed to break the bond between two atoms is called the bond energy, and we measure that in kilojoules per mole. Now if you're asked in an exam what bond energy is, you must say it's the energy needed to break the bond between two atoms. Okay, it happens to be that when that bond is made, then the same energy is released to the surroundings. All right, but in an exam, if they ask you what bond energy is, it's all about breaking the bonds, not making them, even though the same amount of energy would be released when that bond is made. So how do we calculate the energy change, or delta H, for a reaction? I've got an energy profile diagram here again, and we've superimposed the Haber process onto there. So we've got N2 plus 3H2 reacts to give us 2NH3. So our nitrogen and hydrogen are reacting to give us ammonia. And we've seen before that if we know what the value of the bond breaking, the energy we're putting in, so that left hand side, if we know how much energy we need, the activation energy, and then we can also work out the energy released when the new bond's formed, then we can work out the overall energy change. But to do that, we need to know what bonds are in there, so what bonds are in our reactants, what bonds we need to break, and we need to know the value of those bonds in order to calculate how much energy we're going to need. And then also we need to know what bonds are going to be formed in our products and the value of those bonds as well. Okay. So to do this, we need to know the bond energy value of every bond being broken and every bond being made. Luckily for you, you don't need to remember these values. The tables here show some common bond energy values. I've taken these from a textbook we use on this course. The values may differ very, very slightly depending on what textbook you use. But luckily for you, you don't have to remember these, and they'll always be given to you in an exam question. So if an examiner wants you to calculate bond energies or an energy change overall, they will give you the bond energies that they want you to use. Okay. However, in order to calculate bond energies correctly, you do need to be able to balance equations, and you do also need to be able to represent the structure of your reactants and products. So you've got to know what sort of bonds are in your reactants and what bonds are in your products. So in order to support you with this, you need to go back and look at your bonding and structure lessons, and also balancing equations. What we're going to do now then is we're going to look at that Harper process. So we've got the reaction there at the bottom, and I'm going to give you a chance now to see if you can apply what I've said and onto this question and see whether you can actually work out what the energy change would be. Some of you might be able to go ahead with this. You might already think you know what to do. Others you might still not be quite sure what to do, so you can follow in a moment. Right, so this is how we would do it. I've put the reaction at the top of the page, and I've moved those bond energy tables over to the right. And what I said before was that we needed to know the structure of the reactants and products. So what I like to do is I like to draw out what I've got. Okay, and as you can see now, my nitrogen has a triple bond. Okay, it's got a triple bond there between the two ends. And on our table, the nitrogen there, the nitrogen triple bond is 945. That's 945 for the triple bond. You don't have to times it by 3. Okay, that is the value for the triple bond. We've then got the hydrogen with just a single bond between it, and then we've got the ammonia molecule where there's 3 hydrogen and nitrogen bonds. Okay. The next thing I like to do is lay it out with bonds and moles, and I use a dashed line there to just represent the two reactants, and then a solid line to represent the boundary between the reactants and the products. And then we start to put values in. So first of all, that nitrogen triple bond there, we've just said 945, so we can put that in for our bond value there. We've then got our hydrogen-hydrogen bond, which is 436, so we can place that in there. And then we've got 3 lots of hydrogen-nitrogen bonds, which are 391 each. So the next thing I need to do is take into account the moles that are in the equation there. So on the first bit here, the nitrogen, we've got 1 mole, so it's just 1 lot of our 945. With the hydrogen, we've got 3 moles, so we need to times that by 3, so 436 times by 3. And then with the ammonia right at the end, we've got 2 moles of that, so we need to times our original 3 times 391 by 2. And what we can do is work out what those values are. So in the reactants, the bond energy there, the bond values are 2,253, and then in our products, the bond values total up to 2,346. The next step is just a simple calculation. You minus the products away from the reactants, so 2,253 minus 2,346 gives us minus 93 kilojoules per mole. Now then, if you remember back to what we've been talking about previously, about endothermic and exothermic reactions, you'll recognize that this is a negative energy change. Delta H is negative, therefore this must be an exothermic reaction. Okay, so the explanation there to support this would be the energy needed to break the bonds is less than the energy released when the new bonds form. Okay, we've got another question here, a couple of questions. It asks you to write a balanced symbol equation and calculate the energy changes for the following chemical reactions. So this is a typical kind of exam question where you may have to write the equation as well and then work out the energy change. So if you just pause the video now and attempt that question. If you're struggling, we'll go through a worked example of how we do it afterwards. Alright, so the hydrogen and chlorine to make hydrogen chloride. Hopefully you remembered that hydrogen and chlorine are diatomic, okay, they go around in pairs. So your balanced symbol equation should be H2 plus Cl2 gives you 2HCl. We then need to draw out what our bonds look like. So we've got just a hydrogen-hydrogen bond, a chlorine-chlorine bond, and a hydrogen-chlorine bond in the products. So we then look at our bond values. So the HH bond is 436. Our chlorine-chlorine bond is 243. and the hydrogen-chlorine bond is 432. So we then have to consider the moles. We've got 1 mole of hydrogen, we've got 1 mole of chlorine, but we've got 2 moles of hydrogen chloride at the end. So we just add up what those values of reactants and products would be, and then we have 679 minus 864 to give us minus 185 kilojoules per mole. Exothermic or endothermic? Delta H is negative, therefore it's an exothermic reaction. The energy needed to break the bonds is less than the energy released when the new bonds form. The second part here, hydrogen and oxygen making water. Again, hopefully you've recognized hydrogen being diatomic and oxygen being diatomic. So it gives us our reaction of 2H2 plus O2 reacts to give 2H2O. We then need the displayed formula so we know what bonds we're dealing with. Right, and now we can see that in the oxygen there's a double bond. Okay, so remember that in our table that double bond value is the full value. We don't need to times it by 2 because it's a double bond. That is the value of that double bond. So let's put those bond values in. So the HH is 436, our double bond oxygen is 498, and then we've got 2 OH bonds in that molecule of water, so we've got 2 times 464. So looking at the moles, we've now got 2 moles of hydrogen, we've got 1 mole of oxygen, and then we've got 2 moles of our water. So we calculate those values out to give us 1,370 minus 1,856 to give us minus 486 kilojoules per mole. Again, this will be exothermic as it's a negative delta H value, and this is because the energy needed to break the bonds is less than the energy released when the new bonds form. That brings us to the end of the lesson. The next lesson, lesson 4, is chemical cells and batteries. That is a chemistry only topic. So if you're doing the trilogy course, double science, you do not need to go on to lesson 4 or 5. Okay, but hopefully if you're triple chemistry, I'll see you next time.